A little housekeeping. We have a question and answer tab or a questions tab on your panel. If you have any questions throughout the webinar, please go ahead and type them in. I'll make sure to leave a little time at the end so we can go through and make sure that all questions were answered. We are recording this webinar. If you need to come back and listen to it later, it will be posted on both our website and our YouTube channel, and everyone that has attended the webinar will be sent a copy of the slides later this week. My name is Lauren Stewart. I graduated in mechanical engineering from Virginia Tech. I started in custom design and manufacturing, and now I work at Exida. I am a safety engineer here, focusing on our mechanical customers, along with doing a lot of research and publications on stictions and failure rates and the 2H initiative. A little bit about Exida itself before we get right into the webinar. We have worldwide locations, so no matter where you are or your customer is, we have someone close by, someone that can help you or your customer's needs in anything functional safety related. We are divided up into 4 main industry focuses. We have our OEM side, our system designer side, our end user side, and our engineering contracting side. Every industry focus that we participate in, we make sure that functional safety is the primary objective. We have our consulting, we have our software, we have different tools and books and different ways to help you achieve functional safety. We also can be broken up into main products or service categories. And we like to say anything functional safety related we have a part in, whether it's the process, the products, or the people. We have consulting and engineering tools. We have our product certification, our training, our reference materials and textbooks, and our personnel certification. And quickly, just looking at the Exida certification, when your product or the product you buy goes through a product certification, this is the end result. You receive a certificate. The certificate has a lot of great information on it, including failure rates, and we have webinars and blogs deciphering the certificate and all the key parts and information of the certificate if you want more information on that. We have established schemes for functional safety and cybersecurity certifications of systems, of products, of components, and of personnel. Functional safety certification involves a very detailed analysis of both the engineering process and the engineering design, making sure that random failure are accounted for in the failure rate, so you know exactly what the product you're buying or the product you're making can create. We also do cybersecurity certifications involving a detailed analysis of engineering process, the cyber defense mechanisms, and the network robustness. Here's just a quick sample of our reference materials. We publish textbooks, databases, anything related to functional safety. We like to make sure that all of the research we do, all of the our processes, our documents, we like to be an open book. So all of the research and the calculations that we perform, we like to let you know everything that you need to know to replicate those results. We don't want to be secretive. We don't want to be hiding anything. We want to make sure that you know exactly what is involved in functional safety, whether it's the research, the failure rates, the FMEAs, the safety case justifications. Everything we do, we make sure to publish, whether it's in textbooks, databases, or blogs, webinars, or white papers. We also have engineering tools to help in functional safety. We have our Excellentia tool, which is broken down into the HAZOPs, the LOPAs, the SIL selection, safety requirements specification, SIL verification, proof test generator, and life cycle cost analysis. We also have our SIL alarm, which is our alarm rationalization tool, our SillStat, which is field failure data collection and analysis tool, and our CyberFacts, which is our cyber risk assessment tool. So the main reason you're here today is to talk about failure rates and the different ways to get the information and techniques and methods of failure rates, and how that those techniques and methods can apply to your application. We are going to focus on the two fundamental techniques for getting failure rate data, the estimation method and the prediction method. We will go through and talk about each of those methods and techniques, what they consist of, the ways to tell if the data on the certificate is relevant for the application you want to use the information on, as well as examples for each method. We'll then discuss the importance of credible failure rates and why everything is so important to use the correct failure rates. We'll also see why all failure rate information must be published method, and so any data user can see if the method is applicable to their situation, and must validate methods by comparison with field failure data. And then we'll finish up with some comparisons of failure data that's available, examples, and understand what to look for in failure rate information for different application restrictions. So to begin, we're going to look at realistic failure data and how to get failure data. There are two fundamental techniques for getting failure rate data. You'll have your estimation method and your prediction method, and we will look at the differences between both of those in the following slides. But the main, the basic definition is you have your estimation technique, which estimates a lambda or a failure rate based on industry-specific field failure data. Then you have your prediction technique, which is based on test results or design strength analysis. So let's start by looking at the estimation technique or method. This method has three main ways of achieving estimated failure rates. You can have your manufacturer field return data studies, your industry databases, and your end user field failure data studies. And as most things in life have pros and cons, all the methods that we're going to talk about today do. So let's first look at the manufacturer field return data study. This data is great because it is very useful in root cause analysis, and it's real data. It's can be very useful. But there becomes a slight issue when you look at the overall failure rate calculation, as percent returns and actual operating hours are unknown. You also don't understand what each company could consider a failure. Company A, oh, this is definitely a failure, it's going to count in my return analysis, but company B can look at it and say, it was customer misuse, I'm not going to count that, it wasn't my fault. So the definition of a failure could differ from company to company, and even the same company, site to site, could differ on their definition of what is a failure. Then you have your industry databases, which, once again, the data can be very, very valuable if all failures are recorded. it depends on who records it from different companies or even different sites. What is systematic or what is random is often a disagreement, and if you have a detailed taxonomy and operating conditions, this could be extremely valuable information. We're going to talk a little bit later about the Areata database and how that is known as one of the top or the highest quality industry databases ever to be created. We're also going to, another method is the end user field failure data studies. Once again, the data can be excellent site-specific data if all failures are recorded. You have to have a system in place. You have to make sure that you're not disregarding some failures or how that they were found. But many of the existing systems are weak, and many companies and even site to site have different definitions of what a failure can be. So every method in the estimation technique for estimating failure rates has both positive and negative attributes. The most successful failure rate estimation effort to date is the Areata database, and they have been keeping track of offshore and onshore reliability data for many years. They just released in 2015 their 6th edition, and they collaborate different offshore companies in the North Sea. And it provides a high quality data on process equipment in generic categories. So that is great to see all of your information, but it's also hard to know if your system matches exactly what the boundaries of what they're considering a final element assembly. And you have to go through and really pick apart the information to make sure that yours is going to match. But this is a wonderful way to compare your failure rates to real failures that have been analyzed. The second way to predict realistic failure rate data is the prediction method. So once again, the prediction method of predicting failure rates is based on test results or design strength analysis. The test results would be considered the B10 data points, and the design strength analysis would be an FMEA. The B10 data points are based on cycle testing for mechanical or electromechanical products, and it is assumed that the application has constant dynamic operation, which is great for a machinery type application or something that has a continuous demand application. The FMEA or FMEA is a predictive technique developed by engineers that now are working at Exida in the late 1980s. It uses a component database that accounts for design strength versus a predefined environment. And we're going to take a look at both of these methods in more detail. So we're going to start with the B10 failure rate data. It is sometimes called the cycle test failure rate data, and it uses cycle test data, a testing technique developed to determine the end of life for mechanical or electromechanical devices. And this method for predicting failure rates during useful life is described in ISO 13849. The thing you have to watch out for cycle test data, or the B10 failure rate data, is it assumes that all failures are only due to premature wear out and that no other failure rates exist, which is fine for a continuous demand application. Cycle testing is done on a set of products greater than 20 units until 10% of the units under the test fail. And that's where the 10 in B10 come into play. the number of cycles until that failure is called the B10 point. The B10 number of cycles is converted to a time period knowing the cycles per hour in any particular application. And we've done a lot of research on scaling of the B10 point and cycle testing. We've not found any guide, so to say, on how far you can scale, or even how scaling first came to be. When we have done research on different modes of failures and modes of operation, it has been found by many different research firms and scientists that scaling should never be limited to more than 1 cycle per 10 hours. So if you have an application, say a low demand mode application, and you're not expecting to see a cycle every 10 hours, you cannot scale it more than the 10-hour limit. And the failure rate is calculated by dividing the 10% failure count by a period of time. And the failure rate is assumed to be 50% dangerous failure of the total, and 50% of the total failures are safe. So the main point to take away from the B10 failure rate data is that the method assumes that there is a constant failure rate during the useful life, and it is due entirely to premature wear out, and all other failure modes are completely insignificant. Nothing else can happen besides wear out. And as I said, research shows that other failure modes become significant when these products do not move frequently. And some failure modes become significant if the product is static or motionless for even just 10 hours. And where does this become an issue? Where is this in which applications do we really care about this? Well, a main point is like solenoids, valves, actuators. All of these have O-rings or other sealing parts of a product, and many failure modes become significant when the product remains static or motionless for a week or more, some even starting at 10 hours. These failure modes include stiction, cold welding, corrosion, binding, breaking down of the polymers, and most of these failures end up being dangerous. If you have an application where your valve needs to close if there is an issue and the valve is stuck open because of stiction or cold welding, and it cannot shut the process down in a safe or a predictable manner, you then have a dangerous failure that can occur and a major issue. Therefore, B10 data point is not applicable to most applications, including the process industry application. So if you have something like a washing machine or a machinery part that is constantly moving often, therefore you can use the B10 point or the cycle test method and scaling and have no problem. But if you have a process industry application, or you might have an application that is in a low demand mode of operation, you cannot use cycle test numbers and be realistic in your failure rates. And as you can see, these are some just some examples of what can happen because a valve, an actuator, or solenoid remains static. The next method of calculating failure rates, doing with them through prediction, is the FMEA, or Failure Mode Effect Diagnostic Analysis. What happens is you use a component failure rate database with failure rates. The failure modes for each component are chosen based on design and stress and strength. Given a component failure mode, a failure mode of a device is determined. What we do is break down a bill of material and look at every single nut, bolt, O-ring, stem, anything that is in the product. We look at each component and figure out what are the chances of this breaking, how can it break, and if it breaks, will it be dangerous, safe, or no effect to functional safety application? From comparing all of the component failure rates and the failure modes and the distributions, we can then create a component failure mode, the ability of automatic diagnostics, and we are able to compile a whole product failure rate, a product failure mode, diagnostic coverage, useful life can be predicted on the useful life of the components. The diagnostic coverage can be all of the automatic diagnostics calculated to get, and proof test coverage. And the FMEA prediction technique is the study of design strength. And as you can see at the bottom, the FMEA prediction technique, how everything is done, is covered in this book and white paper at the bottom, referenced. One thing, once again, I said there's pros and cons to each method. One thing that you have to look out for when you're looking at FMEA accuracy is the component database. And the accuracy of the FMEA methods entirely depends on the accuracy of the component database. The component database must include failure rates and failure mode distributions of each component as a function of one or more industrial operating profiles. You might have a valve that's going to be always in a clean condition. It's never going to be in a harsh or dirty environment. It's not going to be subsea or offshore. So you need to take into consideration all of those attributes. If you have that same valve that's going to be offshore or subsea, you're going to have to consider different applications and different failure rates. Or what if you have a very dirty or corrosive environment that will be traveling through the valve? You need to be able to look at the different operating profiles and have different failure rates for the different operating profiles that your component might see. As my mom always told me, garbage in is garbage out. So if you have a bad component database and use that in the FMEA, it doesn't matter if you do everything in the FMEA correct and accurate. If you are feeding in component failure rates that are too low or non-realistic or overly optimistic or just a guess, all of your calculations are going to be incorrect. So no matter how good of a process you might have, if you put in junk component database, you're going to receive junk calculations and junk numbers. So what we always suggest is when you are looking at failure rate predictions, you always want to do a validation of the failure rate predictions. So the only way to validate failure rate predictions is to compare the predictions with industry-specific field failure rate data. So here's where we marry the first technique, or the estimations, which is the field failure rate data, to the predictive techniques of the either the cycle test or B10 data or the FMEA. You always want to do a double check when you're dealing with functional safety. You don't want to have the accident. You don't want to have the major misstep because you were overly optimistic or you used failure rates that you trusted but then found that they are not realistic, or the garbage in, garbage out failure rates. Therefore, when you receive a FMEA or you do a FMEA, you have to look at the component database, and they must be based on and calibrated by field failure data specific to the target industry. And this is just the process that we go through for our component databases and the FMEA analysis. So we start and look at the detailed design information. What components are used, what stress factors are being applied to the product application and environment, and we break it down into a FMEA analysis. From the FMEA analysis, we receive the FMEA results. We have the safe detected, safe undetected, dangerous undetected, external leaks, no effects, all sorts of failure rates, and their failure modes along with useful life. We take the results and the failure rates, and we compare them to product level failure rates modes, or failure rates per mode. And we look at that through the component failure rate database. At the same time this loop is going on, there's a second loop. When we look at field failure data, the field failure data is used to compare the FMEA results, but it also is used to calibrate the component database, which we, as I said, we like to be an open book. We make sure that it is a public database. So I learn best with examples and being able to see everything going on. So we're going to look at a couple of different examples. And right now, this first example we're going to take a look at is dealing with pressure transmitters. And this is the total failure rate, not just the failures, the safe failures or the dangerous. This is the total failure rates. So we collected 35 different pressure transmitter designs and compared them to the Areata database, which is a field failure database from the North Sea, and the Dow and pipeline field failure data that is also public. And the Dow field failure data is end user field failure data. And the overall FMEA results, as you can see, it depends on the complexity of the product or the different amount of parts or the way different applications that they can be used in. But you can see that they're all pretty lumped together. You can see that the FMEA results were slightly pessimistic or a slightly higher failure rate, which in our eyes, being a conservative company, we like to see that. We never want to give you a prediction of a failure rate and it be something that you won't hit, or there will be more failures than you're going to assume for your calculations. In doing so, that would be the garbage in, garbage out case. So we always like to be slightly conservative in the failure rates that we publish. And this study is referenced below in a white paper, and it was actually given in a speech. And as you can see, you can find that if you would like to see that more information on just this graph, you can. We also want to take a look at solenoids. So this is a comparison of solenoid valve data. As you can see, we have a couple different FMEAs, and just saying a solenoid can be something that can be misinterpreted. It can be a poppet solenoid, a spool solenoid. There are different types of solenoids that can definitely be looked at. So we wanted to give you examples of both. We picked 2 of the poppet solenoids and 3 of the spool solenoids. along with the exida FMEA average. So all of the solenoids that exida has done an FMEA on, we average together. We compare that to the Areata data, the pipeline company field data, and the Dow field data. And as you can see, the Areata, pipeline, and Dow field failure data are very similar to each other, and that's a good sign that the data collection methods were similar. They are recording all of the failures and not just what they think might be a failure. And because all those three studies don't define exactly what type of solenoid there are, they just say it's a solenoid, we did the average of all of the FMEA solenoids to be able to compare an apples to apples comparison instead of an apples to orange. Once again, the exida FMEA average is slightly conservative, which is a good thing. We want to make sure that you're not going to base calculations that you're doing off of optimistic failure rates. And as you can see at the bottom, you have some other certificate data that come in at maybe 0.01 failures in times or fits, which is 1 times 10 to the negative 9, or 2, or 5. And this is the reason, this graph right here is the reason we always say compare your failure rates. Do a sanity check. Don't just take the numbers that you're given and make sure that they make sense. Don't just take numbers, do calculations, and then have to redo your system when you find out that the numbers that you use are incorrect. So here is one of the certificates that we look at that we are assuming the certificate was, it appears they use cycle testing. So we're going to zoom in and take a little bit of a closer look at this one. So here, this is a solenoid valve certificate. You can see that we are assuming that the B10 method was used. So the B10 number of cycles is converted to a time period by knowing the number of cycles per hour in any particular application. And a failure rate is calculated by dividing 10% of those failures per that period of time. So in this case, as you can see, it's located at the top. It says a high demand mode of operation because there are 2,000 cycles per year is assumed. So using this as a scaling factor, they say that 2,000 cycles per year has a failure rate of 145 failures in times or fit is obtained. Okay. So you go to the bottom of the certificate and it's the same valve, and you can see it deems it is low demand mode of operation, and all of a sudden there's 1 cycle per year being a low demand, and the failure rate is 0.07 fit. Well, if you go through and do some math, you can see that 145 failure fits divided by the 2,000 cycles per year is 0.025. And they want 1 cycle per year instead of 2,000. So now the failure rate is scaled. And this is pretty much the exact opposite of what you should do with realistic failure rates, because low demand mode includes stiction, cold welding, the polymers break apart, there could be corrosion, there could be binding. All of these modes occur in a low demand mode operation that will significantly increase the dangerous failure rates in low demand mode application. In high demand mode application, all you're going to see is wear out. In low demand mode application, there are so many other things that come into play. So it should be the opposite. And as you can see, this one example is right down at the bottom. That's the failure, that's the certificate that we just looked at in detail for a solenoid valve. And here's another solenoid certificate. Some certification reports distributed by different manufacturers include failure rate data that is extremely low. And they say they use the FMEA method, so you have to kind of take a look. And the details of the FMEA method used and the component failure rates used are not available. They always make sure whatever information you use is published. Once again, you have your demand per year. We are looking at a low demand mode of operation, but it's saying it's assuming 10 demands per year, so that must be a typo or something. And the mean time to fail before a dangerous failure rate would be 1.10 fit. So that same certificate can be found right at the bottom here. Even though it claims to be an FMEA, you have to make sure that it matches the sanity check. Compare it to Areata data, compare it to the Dow field data, compare it to FMEA averages that are published. So here's another solenoid valve operation or certificate. You can see that this solenoid is broken down into different applications. You have de-energized to trip and energized to trip with partial valve stroke testing and without for the different variations of the solenoid valve. And it says that you can have the de-energized to trip, energized to trip, normally closed, normally open applications for this series of valves. And it receives two different failure rates, well, multiple different failure rates of dangerous undetected. We're going to take a look at the 188 fits and the 214 fits here. And that's where this solenoid comes into play. Another solenoid certificate, you can take a look at, once again, de-energized to trip, energized to trip. You have a single side solenoid, a double side solenoid, and pilot solenoids, normally closed and normally open. And we're going to take a look at the 999 fits, which is higher than most solenoids would be, but it is a double-sided solenoid, so you need to take that into consideration. And here is that number. So after looking at all of the examples, you might be asking, well, why are there differences? Well, there could be many different explanations. There could be different techniques and different assumptions used in the analysis, like is the assumption made that the device is constantly moving or dynamic? Is the assumption made that the site has absolutely 100% perfect maintenance, that everybody does everything perfectly all the time and on time? It could be that it is very hard, if not impossible, to tell from the certificates and sometimes even from the reports what different methods and assumptions were used. There could be differences if cycle testing was used to determine the data and scaled from a high demand application, scaled down to a low demand time period, and you could receive very low or unrealistic numbers. Their differences could be if some certificates distributed by manufacturers of the mechanical failure rates seem very low, even when it states there's a FMEA used. It appears that if cycle testing was used to establish the component database that uses the FMEA technique, therefore, but no technical papers are presented on it, the source of the information is hidden, it's not made publicly available. That's one thing that you have to look out for, or other methods could be made for the failure rates. So what do? We always suggest check the failure rate data validity. So if you look at a certificate, it's very hard, even for us, if not impossible, to tell if cycle testing was used to determine the data. In some cases, it even says a FMEA was used, yet the results are very similar to cycle testing. And what we've uncovered is it appears that cycle testing was used to establish the component database for use in a FMEA technique type of method. You should look at the manufacturer's self-analysis of warranty data and make sure that it appears to have been used by some certification agencies. They just accept the manufacturer's warranty data, make that the failure rate, but as we talked about, the manufacturers might not consider different things failures from company to company, or even what a failure is. They could, you don't know how many are actually returned. If it is a low-cost part compared to the entire system, it might just be easier to not return it, buy a new one, and put it in. So you don't even know how many are actually returned. Or other methods could be used. Therefore, the only way to safely check the data validity is to use a chart based on field failure data statistics with confidence interval ranges. One way to do this is the SillSafeData.com, and it has been put together to different categories and different types in that category to give you a lower bound and a higher bound in failures per hours or fits. So you have your sanity check. So it's very easy. You receive a certificate with a failure rate on it, and you say, one fit, that looks a little low. You can go to this website and you can take a look at what the lower bound or the higher bound should actually be. And as you can see, there's where the SillSafe data limit for a poppet 3-2 solenoid valve and a low demand mode application is. It says it cannot be below this line without being, maybe it's a continuous demand application, so great, you can use the very low numbers. But if it is not continuous demand mode operation, you need to make sure you're above that line to when you're doing calculations, and to be realistic and to not under-design your system, which could be disastrous. So the main takeaway today is any credible predictive failure rate method must therefore have publicly available detailed description of the method and a comparison of predicted results with industry-specified field failure data compared with an operating profile. And there's a bunch of different examples, some that we've looked at today and actually more. And always do your research if you're looking at different products to use in your system. In a perfect world, you can just take what people give you or the certificates people give you and assume that they've done their job and they've done it correctly, but always double check. You don't want to be the one person responsible for an accident happening. And any FMEA failure rate prediction method must have publicly available complete component database, just published, and a technical explanation on how the component database was created and applicable operating profiles. And once again, there are some examples that you can look into if you want. So right now we're going to go ahead and see if anybody has any questions. And we have a couple. Let's see here. This question is, field failure data from end users may not be available at the time of SIL verification. Can we use the manufacturer's SIL data for SIL verification? You can. I would use it as the sanity check. You can use the SillSafe Data website as a sanity check. You can, if there are field failure data from end users, to use it. You can also use the Areata database. There's many different ways to double check your calculation and your failure rates. So I would consider doing anything that you can get your hands on. Is the SillSafe data the same as Areata? It is not the same. They are very complementary of each other. It is produced by two separate entities, but all of the research we've done shows that the Areata numbers fall in the SillSafe data numbers if you look at the Areata numbers correctly. When comparing your systems to an Areata system, you have to be considerate that the Areata doesn't look at a valve or an actuator. It looks at an entire final assembly unit. It looks at the valve, the actuator, the solenoid, the piping, other components that are bundled up in the same boundary. So if you're reading the Areata book, the beginning of the chapters show everything involved in that boundary. So if you're going to compare just your single ball valve to the SillSafe data or the Areata data, the SillSafe data is the single ball valve. The Areata data, you're going to have to add a ball valve, an actuator, a solenoid to be complementary of it. The next question is Excellentia compiled to SillSafe? Yes, the data in Excellentia is very complementary and the same as the SillSafe data. So if you have Excellentia, you can use the Excellentia data, or if you do not have Excellentia, you can use the SillSafe data website. The SillSafe data website is more of a generic application, which is also, the generics are in Excellentia as well. The Excellentia components actually have much more detailed, but you can get a general idea if you need to. If you're out in the field, you need to quickly look at SillSafe data website to get an idea. It's a very easy method to use. The next question is, what is cold welding mentioned that you used for a failure of a shutdown valve? Cold welding, stiction, the breaking down of polymers all create a binding, whether it's a binding, a metal to metal binding, a metal to O-ring binding. There's different ways that binding can occur in a low demand mode operation for a shutdown valve, a gate valve, any valves, actuators, or solenoids. What happens is that when a bond is not broke, as in a continuous demand application, it starts increasing and increasing and increasing, and it finally gets to a level that it plateaus. Then when, say, the shutdown valve is called into application, it either cannot break the bond, or it tries to break the bond and it takes a little bit to break it, and then it's delayed. So those come into major play in low demand mode operations, something that you hope isn't used often, but you definitely want it to be used when it's needed. So we have, if you want more information on stiction, cold welding, or the binding issue, we have white papers, we have webinars on just that, so you can get a very, and also blogs, so you can get a very detailed analysis. And the next question is, hi, do I need to buy, I think it's database from that website, for example, transmitters, sensors, they list 3 books. The 3 books that you're talking about are the SERH books, I believe, and they are very detailed. They are the same information that is in Excelentia. If you want to look at the detailed components, or not the components, the detailed products, you can look at the 3 books, and that's for final elements, sensors, and I forget what the third one is, I'm sorry. If you just want information as a high and low bounds of a generic field, you can use SillSafe Data. You can, if you have access to Excelentia, you can use Excelentia and you don't necessarily need to buy the books. Oh, it's sensors, logic solvers, and final elements. Thank you very much. So you can use any of those resources to get some of the same information. The SillSafe Data, once again, is more generic. It gives you a high and low bounds, not the I need a ball valve and clean application and get down to the very specifics with a failure rate. So there's different ways to do it. SillSafe Data is a great way to do a high-low comparison. Excelentia or the SERH are a great detailed look at different products. The next question is, how often is the Excelentia SERH data updated? The SERH books were just released earlier this year, an updated version. The Excelentia data in the tool is updated multiple times per year. I'm not sure the exact number, to be quite honest, but anytime you go to use Excelentia and it asks if you would like to be update, that means an update was pushed through and you now, if you update that, have the latest of the data in Excelentia. Are there any other questions? Well, at that point, that's all of the questions we have. If you think of any later, my email address is up on the screen. Please feel free to text or email me, and I will get to it as quickly as I possibly can. I hope that everybody has a wonderful day or evening, and thank you for joining.